We are in section 3.3, curve sketching. This section discusses sketching a comprehensive graph given any function f of x. Steps to graphing a function f of x. First thing is to find the domain of our function. This is where f of x is defined. Most of the problems that we are given are going to be polynomials, which means that the domain would be all real numbers. Or if it is a rational expression or a rational function, it would be all real numbers except where that denominator is equal to 0. 2 says to find any asymptotes, vertical or horizontal. So to find our vertical asymptotes, I'm going to go ahead and label that VA. This is going to be where the denominator, if we have one, is 0. So we're going to set our denominator equal to 0 and solve. And that would tell us where we have vertical asymptotes. Remember, a vertical asymptote is going to be a vertical line, and we usually draw this in by a dashed line. And it's what the function, our graph, gets really close to, but it never crosses or touches. And then horizontal asymptotes, we can look at the limit as x approaches infinity of our function, and the limit as x approaches negative infinity of our function. And these are coming from our chapter 1 notes. Step 3 says to find the first derivative and the critical numbers. And remember, to find your critical numbers, this is going to be where your first derivative is equal to 0, or where our first derivative is undefined. And then create a sign chart for our first derivative and find the intervals where it's increasing, decreasing, and your local extremas. So we do need increasing, decreasing, and local extremas. Number 4 says to find f double prime of x and the possible inflection points, which again is going to be where f double prime is equal to 0 or where f double prime is undefined. We also need to create a sign chart for f double prime and find intervals of concavity. So this is concavity and the inflection points. Remember that your inflection points occur where the concavity changes. Part 6 says on an xy plane, plot the extreme values, inflection points, asymptotes, and intercepts. And so from there, 7 says to sketch with detail each portion of the graph between the extremas and inflection points and asymptotes. And really quick, remember that to find your intercepts, again, this is back from chapter 1. To find an x-intercept, you set y equal to 0, and to find a y-intercept, we set x equal to 0 and solve for the other variable. And then the graph down below this table has what happens if it's concave up or concave down, and then increasing and decreasing, and what those graphs would look like for those intervals. So the next example that we have says sketch the graph of f of x equals negative x cubed plus 3x squared plus 9x minus 10. And so for this, the first thing that we want to note is that the domain for this is all real numbers. It's all real numbers because this is a polynomial, and we always have all real numbers for our domain for any polynomial. So the next thing we're going to go ahead and do is find our x-intercepts and our y-intercepts, and then also look and see if we have any asymptotes. So x-intercept is going to be where we set y equal to 0. And so we'd have 0 equals negative x cubed plus 3x squared plus 9x minus 10. And if you were to try to do this by grouping those first two and those second two, you'll notice that they don't have a GCF that would be factored out that causes those other factors to be identical. So this is going to be too difficult to solve, and this does happen, and there are ways to deal with this, but it does take a lot of time, and not discussed in this course. So we'll just put down too difficult to solve. So we could have x-intercepts, but they would be something probably not nice and pretty, like 3. So it'd probably be a fraction or a decimal. So the next thing is our y-intercepts, and we're set x equal to 0. So we're going to have y equals, and I have negative 0 cubed plus 3 times 0 squared plus 9 times 0 minus 10. And so we get y equals negative 10. And so our y-intercept is going to be at 0, negative 10. I'm going to underline this also because it is difficult to find my answers in all of the work that we have. The next thing is that we have no asymptotes because if you remember, vertical asymptotes are where the denominator is equal to 0, and then horizontal asymptotes are going to occur when looking at those limits, but they're both going to be going off to either negative infinity or positive infinity, so those are not going to occur also. So we have no asymptotes. So the next thing we do is we're going to look at the first derivative and find our critical values. So first derivative is going to be negative 3x squared plus 6x plus 9, and set this equal to 0. Setting this equal to 0, we can solve this. First thing I'm going to do is factor out a negative 3 as my GCF. And so using our guess and check method, multiplies to negative 3 is going to be 3 and 1, and my larger value does need to be negative because my middle term is negative. Again, you can multiply that back out to c. We have x minus 3 equals 0 and x plus 1 equals 0. So we get x equals 3 and x equals negative 1. And these again are my critical values. So definitely keep in mind that. Next thing we're going to go ahead and do is find where our second derivative has possible inflection points. And so we have to take our second derivative and set it equal to 0. So we have negative 6x plus 6 equals 0. And then solving this, I'm going to add 6x, divide by 6, and we get x equals 1. And this is a possible inflection point. So the next thing we're going to do is make a number line. I'm going to make one giant number line. Again, our domain for this problem is all real numbers. And I'm going to go ahead and put in my possible inflection points and my critical values. So I have negative 1, positive 1, and 3. And then I'm going to look at not only my first derivative behavior, but my second derivative behavior. And remember that your first derivative tells you where things are increasing and decreasing, and your second derivative tells you where things are concave up and concave down on our graph. I'm going to go ahead and put some lines in here to separate my intervals just to keep things a little bit more clean as I show my work. So looking at our first derivative and my second derivative, I need to pick a value in that interval to test. And so I'm going to test negative 2. In the second interval between negative 1 and 1, I will definitely test 0. In between 1 and 3, I'll test 2. Bigger than 3, I'm going to test 4. And so for my first derivative, I need to substitute those into the first derivative, which I'll go ahead and circle. And my first derivative, the easiest one for me to look at, is that factored form. And so I have negative 3 times, and then negative 2 minus 3 would be negative. Negative 2 plus 1 would also be negative. So all three of those factors would be negative, which means that my answer would also be negative, which means that it would be decreasing on that interval. The next value we're going to substitute in is 0. So I have negative 3 times negative 3 times positive 1, which would be positive. So that means that this interval would be increasing. The next value we're substituting in is 2 into our first derivative. So we have negative 3 times negative 1 times 3. And so a negative times a positive is still positive. So this is also increasing. And then our last interval here, we're going to substitute in 4. And we have negative 3 times positive 1 times positive 5, which would be negative. So this is also going to be decreasing. Something to note on this is that the critical values that we had were just negative 1 and 3, not at 1. I did put that value in there, but it wouldn't change from increasing or decreasing at that value because that's not a critical value. That value of 1 is a possible inflection point. So our second derivative, now we're going to substitute those into. I'm going to go ahead and circle that. Our second derivative is negative 6x plus 6. And so substituting in negative 2, we get 12 plus 6, which is 18, and that's positive. So that would be concave up on that interval. Substituting in 0, I get 0 plus 6, or positive 6, which is concave up also because it's positive. Substituting in 2, we get negative 12 plus 6, which is negative 6, or concave down for that interval. And the last one, substituting in 4, we do get a negative value, so that would also be concave down. Again, those possible inflection points that we have are only at 1, and so we do actually have an inflection point there because it does change from concave up to concave down at x equals 1. So the next thing to note is going to be, where do we have any relative minimums or relative maximums and inflection points? So our relative min is going to be, if you notice, we go from decreasing to increasing here. So we have a relative min at x equals negative 1. And I'll find my y value in just a sec. And my relative maximum, it goes from increasing to decreasing. So we have a relative maximum at 3. And to find our y values, we do need to substitute those back into our original function that we have up here at the top, and that's because y is equal to f of x. And so substituting in negative 1 and working that out, we get negative 15. And then substituting in 3 into my function f of x, we get 17. So definitely try those on your own to make sure you're able to arrive at those same values. We also have an inflection point because our concavity changes from concave up to concave down at x equals 1. So inflection point is going to occur at x equals 1. And substituting this in to our function, we get a y value of 1. And so I'm going to go ahead and put down all the values that we do know. We have a relative min at negative 1, negative 15. And since our values are so large on our y, I'm going to count every 2 boxes by 5. So negative 5, negative 10, negative 15. And we have 5, 10, and 15. So again, do the best you can. So the first one that we have is negative 1, negative 15, and that's my relative min. My relative max occurs at 3, 17. So putting a point there. And then we have an inflection point at 1, 1. The other value that we had was our y-intercept, which we underlined, is at 0, negative 10. So I will put a point there also. And then I'm going to use what was given to me, and I'll go ahead and use the highlighter for this. But that first interval says it's concave up and decreasing. So we know it's falling, but it's going to be concave up. The second interval is going to be increasing and concave up. So increasing means it's going to rise, and concave up is opening upwards. Concave down and increasing for the next interval. So since it's increasing, it's still rising, but this time it's going to be concave down. And then the next interval that we have is decreasing, so it's falling and concave down. So from here, we can go ahead and put all of this together. And so the first interval is smaller than negative 1 for our x values, and we can see that that is going to go up. And again, we don't know exactly how it goes, but it is going to be concave up and decreasing, so draw it the best you can. The next interval, which goes from negative 1 to 1, so a small interval, it's going to be concave up and increasing. Note that you do have some points to connect, so drawing those in. Then the interval from 1 to 3 is going to be concave down and increasing. So concave down and increasing. And then that last interval from 3 to infinity is going to be concave down and decreasing. And so we have our graph. If it asks for intervals of concavity or intervals where it's increasing or decreasing, we can also list those. So the next example that we have says sketch the graph of f of x equals, and it's 3x over x minus 2. And so this time, instead of having a polynomial like we had for the first one, we have a rational function. And so for this, our domain is not all real numbers. Our domain is going to be all real numbers except, so we have x except where the denominator is equal to 0, which is when x is equal to 2. So x is not allowed to equal positive 2. And that's because that causes that to equal 0. So for this, we're going to first start with our x-intercepts and our y-intercepts. And so our x-intercept is going to be set y equal to 0. And so we have 0 equals 3x over x minus 2, or 0 equals 3x, or x equals 0. And so this is going to be the point 0, 0. And likewise, to find our y-intercepts, we're going to set x equal to 0, and we get y equals 3 times 0 over 0 minus 2, which works out to be 0. So again, we have 0, 0, so I will underline those points just so that way we don't lose those when we go to graph this function. The next thing that we're going to talk about is our asymptotes, and because we have a rational function now, we do have a vertical asymptote, and that's going to be where the denominator, which is x minus 2, is equal to 0. So solving this, this is where x is equal to 2. And our horizontal asymptotes that we can look at for this problem, we need to look at the limit as x approaches infinity of our function, and our function is 3x over x minus 2. And to deal with this, first of all, notice that if you substitute infinity, you're going to end up with infinity over infinity, which is indeterminate form. And so the way that we dealt with this was we divided every single term by the largest exponent that we had on a term in the denominator. And so the power that we have for this one is just x to the first. So dividing all of these terms by x, this is going to simplify to the limit as x approaches infinity of 3 over 1 minus 2 over x. And this 2 over x would go to 0. And so for this problem, we get a horizontal asymptote of 3. And so our function is going to be y equals 3. It's going to be that line, horizontal asymptote, y equals 3. Also note it's the same for the limit as x approaches negative infinity of our function. So we have a horizontal asymptote and a vertical asymptote. Again, I'm going to underline both of those so I don't forget. The next thing that we need to do is find our first derivative. And our first derivative, f prime of x, is going to be using the quotient rule, x minus 2 times the derivative of the top, which is just 3, minus the top times the derivative of the bottom, all over the bottom squared. And so this works out to being 3x minus 6 minus 3x over x minus 2 squared. And so simplifying this again, we just get negative 6 over x minus 2 squared. To find our critical values, we set this equal to 0, multiply both sides by that denominator, and we get negative 6 is equal to 0. And so we don't have any places where our first derivative would equal 0. However, we do see where f prime is undefined. So we'll put down f prime of x cannot equal 0, but f prime of x is undefined at x equals positive 2. So the next thing that we need to do is find our second derivative. And so our second derivative, we have to use the quotient rule again. And here I'll circle the first derivative so we can see that. And so it starts off with the bottom denominator times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which we have to use the chain rule. So we have 2 times x minus 2 to the first times the derivative of the inside, which is just 1, all over x minus 2 squared, or to the 4th power. And so simplifying this, we get, first term is just 0, but we get negative 12 times the negative, which would be positive 12, times x minus 2, all over x minus 2 to the 4th. So you'll notice one of the x minus 2 factors we can reduce or cancel out, and we have 12 over x minus 2 to the 3rd. And so in order to find our possible inflection points, we need to set this equal to 0. And you'll notice that when we do that, we get 12 is equal to 0, which makes no sense. So our second derivative is never going to equal 0. However, we can say it's undefined when x equals 2. So the only value that we need to look at would be when x is equal to 2. However, x is equal to 2 is also not in our domain. It's going to be a vertical asymptote at that value. So we won't have inflection points or points for maximums and minimums. But we need to still graph this, so let's go ahead and draw our number line. And again, the only value that we have to look at is at 2. And I'm going to go ahead and put f prime and f double prime on my graph. So testing something smaller than 2, we'll test 0. Larger than 2, we can test 3. So substituting in 0 into our first derivative, which is circled, we get negative 6 over a positive value since it is squared. So that means it would be negative, which means that this is decreasing. Then testing 3 and substituting in 3 into this, it's also going to be negative, and so this is also decreasing. So from here you can see that we have no relative max or min. The next thing that we're going to look at is the concavity. And so for this, we're going to substitute these into the second derivative, which I'll go ahead and circle down here, which is 12 over x minus 2 cubed. And so substituting in 0, we get 12 over negative 2 cubed, which would be negative. So this is going to be concave down. And then substituting in 3, we get 12 over 1 cubed, which is going to be positive, so concave up. So it does change concavity. However, there is no inflection point because x equals 2 is not in our domain. It can't be a point there. So in order to graph this, we do have some values to put in. And so the only thing that we have is 0, 0, which was our x and y intercept. We also have a vertical asymptote at x equals 2. So I'll go ahead and put that in. So this is x equals 2, that line. And we have a horizontal asymptote at y equals 3. And putting in y equals 3. And so for our graph, looking at those, the first interval that we have is going to be decreasing and concave down. And our second interval is going to be decreasing also, but concave up. And so again, asymptotes are going to be what the graph gets really close to but never touches. So drawing those. And the graph gets closer and closer and closer to it. And then from 2 to infinity, it's going to be concave up and decreasing. Again, it's just a rough sketch, so just do the best you can. If you wanted to, you can find additional values to substitute into the original function and plot those to have more of an idea of the exact location of that part. So we have one more example right below that I'm going to go ahead and circle, and we're going to look at this one together in class.